Hello and welcome to the Unit 9 Section 2 video on key features of exponentials from a graph. So what we're going to do in this section is take a look at a graph of an exponential function, and we are going to determine what some of the key features are. Okay, what are some of the things that we can tell just from looking at the graph? So recall that an exponential function is a function that takes the form of f of x equals ab to the x, where the exponent is your variable. So just as we could identify certain key features in linear and quadratic functions, we're going to do the same here for exponentials. So here's a list of some key features, and we are going to identify them here on this graph. So let's go over what each key feature is. So just like in our other function types, an x-intercept is the point where the graph crosses the x-axis, which you have here. The x-intercept on this graph is x equals 2, or the ordered pair 2, 0. The y-intercept is the point where the graph crosses the y-axis. So that would be located here at y equals -3, or at the ordered pair 0, -3. The domain is the set of all x values. Well, we've got x values going all the way across because remember, we've got an arrow on the left-hand side of the graph and an arrow on the right-hand side of the graph. Since we have an arrow on both sides and the graph is continuous all the way between those arrows, then our domain covers all the x values. So in this case, our domain would be negative infinity to positive infinity. Now our range is the set of all y values. In an exponential function, you are not going to have negative infinity to positive infinity as your range. We got to look at the y values. So you can see that the graph gets closer and closer to -4, but never quite gets there. Okay, we've got this kind of horizontal dashed line, which we'll talk about here in a second. But in any event, we are not ever going to touch -4, so we're going to have an open dot there, or a parentheses when you write it in interval notation, and then our range would go from -4 to infinity because it goes up forever. Our positive interval is the set of x values with positive y values, or in other words, where is the graph above the x-axis. So the positive interval is located to the right of this dotted line because it is at the x-intercept that we start being positive, and we're positive from 2 to infinity. Our negative interval is the set of all x values with negative y values. So the graph is below the x-axis, so that would be on the left-hand side of that dotted line, because everything left of that dotted line is below the x-axis. So it would be from negative infinity to 2. Our increasing interval is the set of x values where the graph increases from left to right. So if we start on the left-hand side of this graph and go to the right, it is increasing the entire time. So our increasing interval here will be negative infinity to positive infinity. Our decreasing interval is the set of x values where the graph decreases from left to right. And in this case, it doesn't decrease anywhere, so we would have no decreasing interval. And then finally, our horizontal asymptote is the horizontal line that the graph approaches as x approaches positive infinity or negative infinity. Okay, positive infinity on the right, negative infinity on the left-hand side. And then our horizontal asymptote is here at y equals -4, okay, because that is where we are approaching on the left-hand side in this case, or as we approach negative infinity, we are approaching -4. And that actually brings us to our end behavior, because end behavior describes what's happening as x approaches positive or negative infinity. Okay, so this should actually say as x approaches positive or negative infinity on one end, okay? So f of x approaches, okay? So f of x approaches positive or negative infinity on one end, and it approaches the horizontal asymptote on the other end. So let's take a look at this example, okay? We're going to do each side of the end behavior with each of these graphs. This is the same graph of the same function. In fact, it's the one that we just had up above. So let's start off by taking a look at what happens when f of x approaches infinity. on the right-hand side. As x approaches infinity, f of x approaches infinity. Okay? So x approaches infinity, f of x approaches infinity. On the other side, as x approaches negative infinity, f of x approaches -4 because we never cross this horizontal asymptote and we never touch this horizontal asymptote. So as x approaches negative infinity, f of x is going to, or closer and closer to -4. So in this case, we do not have an infinity for this statement. We just have a number. So let's do some examples of just identifying some key features. So the x-intercept in this graph, well, we approach on this right-hand side, we're approaching the x-axis. So we're never going to actually touch the x-axis, so therefore we have no x-intercept. The y-intercept is at y equals 1, so 0, 1 is our y-intercept. Our domain, we have all of our x values, negative infinity to positive infinity. Our range, we start from the bottom, we are approaching 0, and we're going to infinity. So 0 to infinity. Our positive interval, across this entire graph, we are positive, negative infinity to positive infinity. And we never go below the x-axis, so therefore there's no negative interval. From left to right, this graph is decreasing the entire time, so therefore there's no increasing interval, and we're decreasing everywhere. Our horizontal asymptote, well, we're approaching 0 on one end, so therefore our horizontal asymptote is at y equals 0. And our end behavior, as x approaches infinity on the right-hand side, we're approaching 0. As x approaches negative infinity on the left-hand side, we're going to infinity in the y. And there you go. That's the key features for example 1. Let's take a look at example 2. So we have the x-intercept. This one is at 1, 0. The y-intercept is at 0, 4. Our domain is all reals. In fact, that's going to be the case with all exponential functions. Your domain is always going to be negative infinity to positive infinity. Our range, however, if we start from the bottom, we're coming from negative infinity, and we are approaching 8 at the top, so negative infinity to 8. Our positive interval, we're positive on the left-hand side, so from negative infinity until we get to our x-intercept of 1, and then we're negative from 1 to infinity. That's where we're below the x-axis. We're increasing nowhere because this graph is decreasing everywhere. Our horizontal asymptote, where we're starting to level out on the top, is at y equals 8. So our end behavior, as x approaches infinity on the right-hand side, f of x is going to negative infinity. As x approaches negative infinity on the left-hand side, we're approaching 8 in the y. All right, let's take a look at example 3. So our x-intercept, it looks like everything's going to be below the x-axis. We're going to level out at y equals -3, so we have no x-intercept. We do have a y-intercept of -4, so 0, -4 is our y-intercept. Our domain's all reals. Our range, negative infinity to -3, which is where we start to level out. We're not positive anywhere. We're negative everywhere. We're increasing from left to right in this graph, so negative infinity to positive infinity, which means we're decreasing nowhere. Our horizontal asymptote is at y equals -3. That's where we start to level out our graph. So our end behavior, on the right-hand side, as x approaches infinity, f of x approaches -3. On the left-hand side, as x approaches negative infinity, f of x approaches negative infinity as well, because our graph's going down. Let's talk a little bit about growth and decay and how some key features compare when you take a look at a growth function versus a decay function. And the growth and decay is the only difference between those two graphs. Okay, so remember, we have exponential growth when our b value is greater than 1. That is the base of our exponent. And then it is decay when you have b between 0 and 1. So let's compare the similarities and differences of a few key features between growth and decay. Keep in mind here, the only difference that we have happening here is our growth and decay. Everything else is the same. So in both cases here, our domain is negative infinity to positive infinity. In both cases here, our range is 0 to infinity. Our x-intercept is none in both of these. Our y-intercept is at 0, 1 for both of these. Our horizontal asymptote is at y equals 0 for both of these. But our end behavior does change. As x approaches infinity, f of x approaches infinity on the right side for our growth. We're approaching 0 on the left-hand side. But for decay, it flips. On the right, we're going to 0, and on the left, we're going to infinity. So end behavior is where our difference really lies here. And our increasing and decreasing is also obviously going to be a difference here. In a growth function, we're always increasing, never decreasing. In a decay function, we're never increasing, always decreasing. So I just kind of wanted to point out a few of those similarities and what the main difference is between growth and decay. Let's finish out this section talking about average rate of change. Now, the nice thing is, if you went through Unit 8 with quadratics, the method for average rate of change for exponentials is going to be exactly the same. So this is mainly going to be a little review section here to wrap up this part of the unit. So recall average rate of change is a ratio that compares the amount of change along the y-axis and the amount of change along the x-axis between 2 points on a function. So you remember the formula y2 minus y1 over x2 minus x1. We're going to be using that whether you have an equation, graph, or table. So let's start with an equation. You're going to substitute the first x value into the equation and solve for y. This is going to give you your first point. Substitute the second x value into the equation and solve for y. This gives you your second point, and then plug both of your points into your average rate of change formula. So let's do this with a couple of examples. So in example 4, we're going to find the average rate of change for the functions over the given interval. So remember, the interval gives you your x values. So for a, we're going to plug in 2 for x, and when you do, you're going to get 2 squared, which gives you 4. Then we're going to plug in 4 for x, and 2 to the 4th will give you 16. And you may want to use your calculator to find some of this, okay? So our first point is going to be 2, 4 from the first thing that we found. Our second point is going to be 4, 16. So that's our x1, y1, our x2, y2. We're going to plug it into our average rate of change formula, and then you just subtract the top, subtract the bottom, get 12 over 2, which gives you 6. And that's all there is to it, okay? Just a little bit of doing some basic math. For b, we are going to plug in -1 for x, and that gives us 1/2 to the -2. You can put this in your calculator, and it'll give you what the value is, but what it will give you is 4, okay? Because 1/2 to the -2 is the same as 2 to the second power. You flip your fraction to get your exponent to be positive. 2 squared is 4, okay? We put in 1 for x. You get 1/2 to the 0. Anything to the 0 power is 1. So our 2 points are -1, 4, 1, 1. Plug that into your average rate of change formula. Evaluate the top and the bottom, and you end up with -3/2. Finding the average rate of change from the equation is going to involve the most work because you have to plug in your 2 x values to find your y's. It gets considerably easier when you have to find it with a table. So to do this from a table, you're going to first find your first x value and find the corresponding y value. That's your first point. Then go to the second x value and find the corresponding y value. That's your second point. And then you plug them into your average rate of change formula. So this is basically just read the values off the table. x1, y1 is going to be 0, 4, because 4 is the y that's with the 0 in the table. For 2, 16 goes with it. So you got your 2 points, you plug them in, subtract the top and the bottom, you get 12 over 2, and that gives you 6. For b, negative 2 has 26 with it, negative 1 has 2 with it. You plug those in, evaluate the top and the bottom, and you end up with negative 24. So doing this with a table, considerably easier. Finally, doing this with a graph is a kind of in between. You have to do a little bit of work to find your y's, but it's not too difficult. You're going to find the first x value on the x-axis and follow the vertical line until you meet the graph. And then you find the corresponding y, and that gives you your first point. Do that for the second x value as well, and then plug both points into your average rate of change formula and simplify. So for example 6 here, for the first one, if we're going to negative 4 on the x, you're going to follow that down on your graph until you hit the function, and then you're going to follow over to your y. So the y that goes with it is negative 5. Then you're going to go to negative 2 on your x, follow that down to your graph, and follow that over to your y. So negative 2 is your second, and then from here, you're just going to put it into your average rate of change formula and do the math to find 3/2 as your answer. For b, we're going to go over to 1, down to your function, and the y value that goes with is negative 3. Then you're going to follow 3 over. We're already on our function, so 3, 0 is your second point. Plug those in and do your math. 3/2 for this one as well. All right, so that's a look at key features and average rate of change for exponential functions. Many of these things feel familiar because we did them with quadratics, so hopefully a lot of this was reviewed for you. Coming up in the next section, we're going to talk a little bit about graphing exponential functions and how you go about creating a graph.